0.12.
Go ahead.
It is given E is equal to 120 pi cosine of 6 pi times
125.
yes
Go ahead. Cosine
of 6 pi times 10 to the 6th t minus 0.08 pi y in the AZ direction, and H is equal to
looking for H probably.
H is equal to 2 cosine 6 pi times 10 to the 6th t minus 0.08 pi y in the AX direction. Find mu relative and epsilon relative.
All right, they just want the material parameters. All right, first, one look at that. Is that a lossless wave, class?
Yes.
How do you know?
No attenuation.
There is no e to the minus alpha times y, right? By the way, which way is this propagating? Let's try this. We're going to go through it. What is the direction of propagation? The unit vector and direction of propagation? Take a look.
Positive y.
Positive AY, right? So it'd be AY. All right, next. What is omega by inspection?
2 pi times
6 times pi times 10 to the 6th, right? That's radians per second, right, class? All right, what's beta by looking, by inspection? 0.08 pi, right? Now, when you look at this, it's non-magnetic, right? Sorry, it is not lost. Now, we just, at this point, figuring out material parameters is pretty straightforward. You know, since it's loss, there's no loss on this one. You know that in general, gamma is equal to the square root of j omega mu times sigma plus j omega epsilon, right? And gamma is equal to alpha plus j beta, right? Are you all following me? I'm just putting out the reasoning behind it. Now, if you look at this, I know it's lossless, right? Because that's sigma 0, isn't it, class? So if sigma 0, I really have this, and that means gamma is equal to 0 plus j beta. And you can see that's going to be equal to, I got j omega times j omega brings, and the square root of that is j omega times square root of mu epsilon. I've done this before, but I'm making sure you see the entirety of it. You all with me? Everybody? All right. I'm going to get rid of the j. Therefore, beta is simply omega times square root of mu epsilon. Now that's always true in a lossless medium. Always true for constant frequency. If it's driven with a cosine or sine. Everybody follow me on that? All right. Going a step further, beta is equal to omega times square root of mu naught epsilon naught times square root of mu relative epsilon relative, right? Only thing I'm doing here is just making sure you see the reasoning. This is where you go to if it's lossless, always. I come here, and I can see I have omega, I have beta. Square root of mu naught over epsilon naught is 1 over c, isn't it, class? So now I can find out that, and I'll put it up here, I have beta over omega is equal to, well, really, I'm going to go ahead and just say this square root of mu naught epsilon naught might as well just be replaced by c right here. Y'all agree with that, class? I'm not trying to do anything too fast. Y'all follow me on that? I'm just getting rid of things I don't need. So 1 over the square root, or I could say c is equal to 1 over the square root of mu naught epsilon naught. And so square root of mu naught epsilon naught was up top. I'm replacing it by c. So I can come over here and just put c over here, and that's equal to the square root of mu relative epsilon relative. Right? Now we have beta, we have c, and we have omega. So we have the square root of mu relative epsilon relative. Do y'all follow me? I'm gonna go ahead and just take this quantity and square it. And now I have mu relative, epsilon relative. You all agree? I mean, there's really, just gonna show you, you're gonna get two equations, have two unknowns, and solve for them both. All right, next thing we know is the ratio of the magnitude to e to h, right, is the intrinsic impedance to the medium. That's equal to the ratio of, in this case, magnitude of E over magnitude of H. And the material parameters that involve eta, the general form is square root of J omega mu over sigma plus J omega epsilon, right? That would be for any medium at a constant frequency, including sigma. You all follow me? It's lossless, isn't it? If it's lossless, what do we do over here? What's the one thing we change? Sigma is 0, right? I just erased it. Now you can see the J omegas cancel, and I get simply the square root of mu naught over epsilon naught times square root of mu relative over epsilon relative. I want to make sure you see the logic. Right? Now, what is the square root of mu naught epsilon naught? It's called the intrinsic impedance of free space, or eta naught, or 120 pi. So now I can say this, the ratio of e to h, I'll put it down in 1 second, is equal to 120 pi times the square root of mu relative over epsilon relative. Well, E is 120 pi, and H is 2, so that's going to be, the ratio of that is 60, isn't it 60 pi? Y'all follow me? Okay, I take 60 by 120, and I get 1/2. And that's equal to the square root of mu relative over epsilon relative. And that means 1/4 is equal to mu relative over epsilon relative. Now I've got two equations. I didn't put in beta and omega and C here, but I might as well. So beta for this one was 0.08 pi. And omega was 6 pi times 10 to the 6. And then C is the speed of light. I'm going to go through the math, but I want you to just see I'm plugging in things that were identified earlier, right? No tricks on this one. If you take a look at this, I'll get rid of the pi. Do that anytime I can. I have 10 to the 6th and the 10 to the 8th. That's really 10, or 100 right there, 10 squared. And then I have, so I'll put 100 here. Then I have 3 over 6, and that's 1/2. So I multiply this by 100, makes that 8, right? 8 over 2 is 4. Keep breaking it down. Squared is 16, so this is 16. Now, I don't care how you do it at this point. I have the product of the two being 16, the ratio of the two being 1/4. How do you want to do it from here? Well, mu r is what? 16 over epsilon r, correct? I'm just going to stick it over. You all follow me on that? So mu r right here would be 16 over epsilon r is 1/4. I can therefore take epsilon relative squared is really going to be, but first of all, do you all see what I've done here before I just move along? Y'all with me on that? So what is it going to be? Well, epsilon relative is what? If 1/4 is 16 over epsilon relative, that's going to be 16 over 64, right? That means epsilon relative is 8. Is it a class? Is that right, by the way? I don't know. I don't know what Wentworth's book is, but I assume that's right. What? I think it's right. Okay, now, but do you understand, pardon me? The real thing about this problem is starting here and knowing really some basics. One is the ratio of E to H is the intrinsic impedance. Second is how to get beta and omega and identifying its losses. That's it, just identifying from the waveform what, I mean from the mathematical description what omega and beta are. And it's those kind of problems, if you don't do, you know, might say a bunch of them, sometimes you start fumbling around like, I don't know what to do. I'm looking for something I don't even know how to find. Okay, another question. That's a good problem. Anybody? I forgot how many I gave you. I didn't give you that many, did I?
No.
They were straightforward, I think. And I asked you in all those to find, I think, the fundamental velocity, intrinsic impedance, wavelength, I'm not even sure what else, but I wanted you to make sure you could find the values, basic values, in all the problems I gave you. Okay. Any other questions before we go? Yeah.
Can you do a 6.1?
6.1?
6.19.
Sure. Go ahead and give it to me.
It says in seawater, a propagating electric field is given by E of C
E equals what?
20 E alpha to the negative alpha Z
E 20 to the minus,
E
go-
alpha
E minus alpha Z, go ahead.
times cosine of 2 pi plus 6 G minus beta Z plus 0.5.
Plus what?
Plus 0.5.
0.5.
Okay. What direction?
In the AY direction.
Go ahead. That's in seawater?
Yes.
Go ahead.
And then assuming epsilon equals 0, find
Oh, assume what?
assume epsilon, it's got like two colon, or two quote.
Epsilon double prime.
All right, epsilon double prime is a loss tangent. We're gonna, it's a loss term. We're gonna talk about that today. So there's no loss. That's the thing about that related to dielectric losses. But there, in seawater, there will be a conduction loss. Go ahead.
Okay, and then it says to find alpha and beta and the instantaneous form of H.
So this is in seawater.
Yes.
All right.
That also gives you the epsilon relative for seawater at 72.
72? It's actually 81, I think. It's closer, but epsilon relative is 72. Okay.
And then sigma is 5.
Sigma is 5. Problem's over now. The minute they give you that, it's a done deal because now you have, it's non-magnetic, right?
Yeah.
It is, all right? If it's non-magnetic and you have epsilon relative and sigma, and you can get the frequency, you can get eta, right? You can also get alpha, and we're gonna get all of them, all right? But this is one of those problems. The only thing it's doing is making you aware of what you need to see in order to solve something like this and get all the properties, all right? Really, it's alpha you want in that one, if you take a look at it. So when we look at this, let's start, just check boxes with me. What's omega by looking?
2 pi times 10 to the 6th.
It's 2 pi times 10 to the 6th. It's radians per second, all right? After that, if we know the frequency right here, right? We know omega. We know F would just be this divided by 2 pi, or it's 10 to the 6th hertz, right? Just showing you this, right? All right, now after that, what I'm gonna do is something fairly simple. When I take a look at the actual value for the propagation constant, which is alpha plus j beta here, that's equal to the square root of j omega mu times sigma plus j omega epsilon, right? Y'all give me that? Here's where we're gonna see something. I believe Wentworth chose these values for a specific reason, but I'm gonna see if I'm right about this. So I want you to take a look at these two terms, sigma and omega. So sigma has a value given as 5, right? That'd be Siemens per meter, 1 over ohm meters. And now, what is omega epsilon equal to? Well, omega is 2 pi times 10 to the 6. Here, I have to multiply by epsilon, which is going to be 72 times epsilon naught. And epsilon naught can be given as 1 over 36 pi times 10 to the minus 9. Now the only thing I'm doing here is I'm getting this term and this term separately, and I'm going to contrast them. If sigma is much, much bigger than omega epsilon, I can ignore omega epsilon. You all follow me? Everybody?
You say that one more time.
If you take a look at this, I've got sigma here, and right next to it is omega epsilon, right? Well, if sigma is orders of magnitude larger than omega epsilon, I'll ignore omega epsilon, right? That J doesn't do beans as far as anything, it's a phase term. Then if I do that, what I can do is get a simple approximation. But first, let's see what the values are. Take a look at this for 1 second, all right? I put the 36 pi down there because I see I've got 2 pi on top. You all follow me? I want you to take a good look. The reason for it, right? So take a look what this is. The 2 pi and 36 pi really becomes 1 over 9, doesn't it, class? Agreed? Now, after that, I got 10 to the 6, 10 to the minus 9. That's 10 to the minus 3, correct? I'll put it down here. Now, I got 72 by 9. 8, right? Pardon me? Are you all following me on what I'm doing here? So this is really, all right, now look at this. Would you say that sigma is much, much greater than omega epsilon? How many see that? What do we call that? A good conductor. Do y'all remember me talking about this? Yeah. This is a very good conductor. Sigma is what? About 3 orders of magnitude larger than omega epsilon, right? So you can, for all intent and purposes, ignore the J omega business here. What does that make this then? Well then, this is equal to the square root of J omega mu times simply sigma, isn't it, class? This is an important part I'm going to talk about for next. Y'all with me? This is a perfect lead into what I was going to talk about today, one of the things. Y'all see the reason? All right, now, here it gets interesting. When I take a look at J is really e to the J pi over 2. If you think about the way it's normally written, J is, I know, the square root of minus 1, but J is just what? It's really one at an angle of 90 degrees, isn't it, class? That's J. Y'all follow me? All right, well, what's the square root of J? That's e to the J pi over 4, isn't it? Want to make sure you say it. Do you all agree with that? If you take square roots, taking this to the 1/2 power, so it's just pi over 4 instead of pi over 2. You all follow me, class? All right, use Euler's identity here. What do you get? You get the cosine of pi over 4 plus J of sine of pi over 4, don't you? You all follow me? E to the J theta can be expanded as cosine of theta plus J sine theta. Theta in this case is pi over 4. All right, pi over 4 is 45 degrees, right? What's the cosine of 45 degrees? 1 over square root of 2, isn't it? What is the sine of 45 degrees?
Same thing.
1 over square root of 2. So I can render this as simply 1 plus J over the square root of 2. You'll see why in a second. Y'all with me on that, class? All right, now coming back over here, you see I have square root of J. Y'all see that. The rest is real in here. So square root of J is 1 plus j divided by square root of 2. And then I get the square root of omega mu sigma. Some of you remember me doing this. I'm just rewriting it right there. Now, I'm going to take the square root of 2 under the rest of this business. So I just make this, okay? Y'all follow me? All right, what is omega? If I take a look at this, isn't this 1 plus j? And then if I take a look at this, it's square root, well, omega is 2 pi f, isn't it? Can you all see that? So if you put in 2 pi f by 2, you get pi f and then mu sigma. And what you'll find out is that is alpha plus j beta, or gamma, for a good conductor. I mentioned this before, but this is true for a good conductor. All right, and that means that alpha is equal to beta, and it's equal to the square root of pi f mu sigma. And that's important, because in a good conductor, alpha is equal to beta. Do y'all follow? And it's equal to this. Now, can we get that value from what we have? Take a good look. Convince yourself one way or the other. How many think yes? How many don't know? How many won't respond? I look at people, I'm not going to raise my hand. Sue me. All right, so what's this going to be? It's the square root of pi, right? What's f? You all see it? 10 to the 6, isn't it? Times 10 to the 6, right? Times mu, well, it's just mu naught, which is 4 pi times 10 to the minus 7th, right? Times sigma, which is 5. So what do you get for alpha and beta in this case? It's really this easy. Just do it. 4.44. Is that what you guys are getting? All right, 4.44. And it's either Napiers per meter or radians per meter. They're the same exact units. All right, so now I have alpha and beta, which is good. That means I've got alpha and beta in this equation, right? All right. They want H, don't they? I might be wrong.
Yes.
All right, so now, can I put this in terms of a phasor?
Yes.
Yeah, sure. Phasor form would be what? Magnitude would be 20, right? Then you would have what? E to the minus alpha is 4.4 z, right? And it would be times e to the minus, and what is beta? 4.4 times z. Gotta have a j there. Now I could combine those, but I broke them up separately just to show you. This is attenuation, and this is going to be the propagation, or it's going to be the wave number. And it's going to be in the AY direction. Now that's E. What is the direction of propagation starting? A unit vector in the direction of propagation, class? Say again? Can you all see that up right? It's in the Z direction, right? Y'all follow me? It's propagating in the Z direction, so it would be AZ. Y'all follow me? All right. Got that. Now, do you remember those two little shortcuts I gave you? If you have E, how to get H in the phasor domain, or have H, how to get E if it's a propagating wave? I'm going to remember that. All right, we've got E. To get H, what do? It's 1 over eta, we didn't get that yet, times the unit vector in the direction of propagation. We've got that crossed into the E field in the phasor domain. You'll notice that we have the E field in the phasor domain. Now we need eta, right? Eta is the intrinsic impedance. Use the fundamental definition. And let me erase this over here. This worked out perfectly. not by design either. I didn't plant these questions, I promise you. But if I was good at it, they would be the questions I planned.
We also have to take the phase shift into account.
We will. I'm sorry, you're absolutely right here. What he's saying is, this should be minus 0.5, because you see this quantity beta z here appears here. The minus sign is here. Y'all follow me? It's minus j, there's this, but that's a positive, so I make it minus 0.05. Y'all follow me? All right. Okay, now, and thank you for that. I need to get eta. So how do I get eta? Use the fundamental definition. Square root of j omega mu over sigma plus j omega epsilon, right? But what am I going to do in that case? There's one thing I just showed you about the magnitude of sigma and omega. Sigma is orders of magnitude larger than omega epsilon. Do y'all follow me on that? So I'm going to just say this is approximately equal to simply the square root of j omega mu over sigma. Now I want to tell you something. If you went ahead and put all the values in there, you'd still get the right value. Right? Well, I'm not really sure, but I programmed this into my calculator, so I'm just going to let it rip. You'll still get the right answer. This is an approximation that makes my life a little easier usually. So that's the reason I do that. Now, when you do this, the square root of j can be rendered, and they do it either way, e to the what? J pi over 4, or 45 degrees. You see you got j in there? I could break it out as 1 plus j over square root 2, but I'm going to do it this way here. It's a little easier to deal with. And then I have this. I have the square root of omega, and omega is what? 2 pi times 10 to the 6th, right? Times, or it's actually it's omega times mu times 4 pi times 10 to the minus 7 over sigma, which is 5. So if somebody can give me what this is, it'd be great. That one, oh boy, it's small. Anybody? It's about 1. What do you guys get for that? Pardon?
1.25.
Anybody confirm that? 1.25?
That's it.
So this is times 1.25. Now, I come over here, and I'm going to get h in the phasor domain first. So h in the phasor domain is 1 over 1.25 e to the j pi over 4 radians. Then it's times AP, and the direction is plus AZ, crossed into the E field. There's the E field. That's a cross product times 20 e to the minus 4.4Z times e to the minus j 4.4Z minus 0.5. All right, that I'm writing the whole thing down. Can you all follow me why I'm doing? Can you all see it back there, guys? All right. Now you can go ahead and see that this is going to be h equals, let me deal with the constants first. What's 20 over 1.25? 5/4, so it's 16?
Yeah.
That's right. So you get 16. Now I'm going to put the next one, it's going to be the attenuation e to the minus 4.4z. Now, when you take e to the j pi over 4 upstairs, from the denominator to the numerator, it's e to the minus j pi over 4. Do you all agree with that? So then, for these terms, I get e and it's gonna be to the minus j quantity 4.4 z minus 0.5, but then this is gonna be e to the minus j pi over 4, so this is gonna actually add right here to the plus pi over 4 here. You all follow me? And it would be in what direction? The E field is in the AY, right? So cross, there should be an AY here. So when I take AZ cross AY, I get minus AX, right? Minus AX. And that's in the phasor domain. Do you all agree with that, class? See it? In the far back. Guys? All right, so that's in the phasor domain. Let's put it in the time domain right under here. Erase this E field. So what do I do to get it in the time domain? Got a phasor quantity. If you want a time domain quantity, technically we take the real part of e to the j omega t times the phasor domain quantity, right? That's the definition of how you do it. But really and truly, we're taking what? You're gonna take the waveform, it's gonna vary as a cosine, right? The real part, the e to the minus alpha z comes out in front of it. So here's what we're gonna get. Just bear with me. Definitely gonna get 16. And by the way, here's something else I can tell you. If you don't like the minus there, you can add 180 degrees to this. You can either add plus or minus pi inside there, and it can get rid of that negative if you don't like it. Y'all follow me on that, class? I'll leave it there for now. I don't know how liquid does. It doesn't matter. But it's going to be minus 16. Then it's e to the minus 4.4 z. Then it's going to be a cosine of 2 pi times 10 to the 6t minus 4.4 z minus, or I'm sorry, plus 0.5 and then minus pi over 4. And that would be in the AX direction. Interesting problem. You have the solution? Yeah.
That's right. I was just wondering, for eta, how come you can't use square root of u naught, or u relative of epsilon?
Can anybody answer that besides me? Hear that? Because sigma is so large. It's not a lossless problem. If it was lossless, then you could use that. But it is not lossless. Right? And that's sigma. The minute you see sigma or alpha, that it's non-zero, you've got to go through the whole 9 yards. You've got to check the value to see if it's a good conductor or not. Sometimes it's not a really good conductor, so you got to use both sigma and j omega. All right. So that's, well, that problem, it showcased everything you need to know. By the way, if I asked you for the velocity, I don't think, is it asked for in this problem or not? If you wanted the velocity of propagation, the phase velocity, what would it be? What's the fundamental definition of phase velocity?
Omega over beta.
Right. So what would it be in our case? Well, omega is 2 pi times 10 to the 6th, right? And beta is what? 4.4. So tell me, what do you get for that? A little over 10 to the 6th meters per second. What do you get? 1.42. What's the speed of light in a vacuum? 3 times 10 to the 8th. You notice orders of magnitude slower than the speed of light is in a vacuum. That's important to remember. All right. Lossy things, lossy materials, or high dielectrics, in this case both, slow things down a great deal. Remember that in terms of the velocity of propagation. Just for kicks, how do you get wavelength? Pardon me? He's right. Don't use C over F. It's 2 pi divided by beta, right? Now beta in this case is 4.4 as well. All right, so that's a no-brainer. But in free space, the wavelength would be much, much, much more. Okay. I was gonna cover lossy dielectrics, but I'm about down to the 10-minute marker. So I'm gonna move people around, spread out as much as you can. And here's a second.